Hi there, welcome back. We're into part 2 and hopefully the last video on the repair of the Gryphon, and I'm actually pleased to report that it seems that both channels are now complete. Now, if you recall from the previous video, and it's been such a long time ago, I'll put a link above if you want to go and look at that. This thing was a total disaster. It was one of those things that I honestly didn't understand why I got myself into it. I like a challenge. This one was quite a challenge. But like all challenges, the harder they are, the more satisfying they are when you finally succeed. And I think I have. Anyway, what I had here was an enormous number of tracks that had been ripped up, components that were burnt out, and quite honestly wasn't sure which. Because when I did some of the tests, I couldn't really tell whether the problem was the component or the actual tracks. So this side took quite a bit more to do than the other side, which I showed you in the last video. And it took quite a lot more in everything, time and components. Now, this repair of the tracks, that's something I just want to touch on. It was a hell of a lot harder than I thought, because the method I was trying to use in a double-sided board like this one, it worked for a while, and it worked in some cases, but not in all. Let me show you. What I was using was this copper tape. Now, you can buy this in quite a few different widths. I chose the thin one because I didn't need more than that. Obviously, all the tracks that I needed to cut were a damn size thinner than this, generally less than a millimeter. So this is, it's a sticky tape, so you rip off the back and you can stick it on, and then you can solder on there quite easily. And it's actually a very, very good method to repair tracks, and some of them I managed to do with this. Now the problem is that when you're doing a lot of turns, you either cut this track exactly the right shape and stick it down, or you could try the other method, which is to do small bits and make the whole path with little bits and stick them together. The problem is the minute you put heat on them with a soldering iron, they actually lift. The glue is not that strong, so it actually does lift. And what you need to do really, if you've got a short length, from one component to the other, and you put the components through, the legs of the components tend to hold it down, so it does help. So in those cases I managed it, but otherwise I can't say that that method was the best. I ended up doing what I could, and the result is actually a lot better than I expected. You may be able to see there, you can't do much about those pads at the top that were ripped out. A lot of them aren't necessary. They're not really making contact. A lot of these transistors were swapped out, even though they perhaps were not completely dead. And the reason is that this thing had been incredibly stressed, and I didn't want to risk it popping again just because I'd left out one transistor. So all these transistors, in fact, on this section, all the transistors were replaced, just to be safe. All these were replaced. The Zener diodes were replaced. I've had so many cases of things going pop because a Zener is leaking or something's wrong with it, that I've just learned my lesson. Now, you'll also notice that this op-amp has been put on a socket. The op-amp was acting quite erratically as well. Now this is the DC Servo Op-Amp, and I decided to put a socket in there just to make it easier to remove if I needed to. Other than that, other than transistors, resistors and diodes, well, there's not much else, is there? Some of the capacitors are okay. Other than that, everything was the same. Now on the back, there is still obvious signs of the previous repairs. You can't really do much with that, but the tracks are actually there. This needs one final cleaning. That thing there had enormous trouble with So I ended up having to do a little bit of what they did in the other one, unfortunately. But anything that was sort of flying over has been removed. Let me see if I can show anything else close up. There are some in the middle of those three there that were actually replaced with a copper tape. Can't see that too well. And yeah, well, what can I say? It took me a hell of a long time to do this. It took a hell of a lot of time just to build up the motivation really to get started on the second channel and to continue. That's why it's taken so long. Obviously, I've done other things in the meantime. But that's why really it's taken so long to get to this point. But let me show you what the procedure involved. And here we have the all-important block diagram or interconnection diagram for the input board. This is for the one channel. In this case it's the right channel, but they are identical. Now this is only the input board, so the board that I've been showing you has two of these, one for left, one for right. This is important because what it does do is it shows us how the various parts of the schematic link together, and it makes it easier to do fault finding on the board itself. Now it has various discrete components, as you can see. For example, you have the input relay over here. This is the XLR connector. It shows you how this connects to the inputs in general. What you have here is a pot that allows you to adjust the offset between the positive and negative signal lines. It then shows you the various parts of the schematic. You've got the power supply showing the inputs and the respective outputs. You've got power in, power ground, and power negative. That would be plus 70 there, that's minus 70 there. Then you get a regulated output, plus and minus, coming out there. There's a 24 volt output and a reference 24 volt output over there, and the plus and minus 15 volts for the op-amp circuits. Then if we go down, we get the input amplifier itself with the positive and negative input. It takes the regulated positive supply as an input and the negative regulated supply as an input as well. It produces a drive signal, positive drive signal and negative drive signal. This would then go to the actual power amp board. Below that we've got the DC servo, which produces a DC offset signal over here. And if you follow that, it shows you that this actually goes to the two inputs on the input board, and that comes through there from the XLR. So what it does is it adjusts the DC offset that may exist or is required to keep a stable output. There's a DC detect signal here that tells you that it's detected DC on the output, which would have to do something to protect the speakers, and in this case we can see that it goes to the relay driver as a DC detect. That obviously would disconnect the relay that's got the speakers on it to save your speakers. Back to the servo, here we've got a sense signal. That's the sense signal from the output. There's the plus and minus supply and ground. Now if we go to the relay driver, there's the relay out, positive and negative, input relay control, power supply section coming in, DC detect signal from the top board, and also the temperature sense that comes from the temperature sensing on the heatsink of the output board. So that gives us an outline of how this whole thing fits together, and it's very important because it makes it a hell of a lot easier to actually see what you're doing. This is the first stage, the regulated power supply schematic. As you can see here, you've got three very distinct sections. This is the first one over here, there's the second one over there, and then this is the final part of the schematic that's of importance here. Now it makes it easier that you can actually treat each of them separately. Let's have a look at the first one. What you've got coming in here is you've got plus 70 volts, minus 70 volts, and it's going to the circuit here. If we follow through to there, we see that it's actually the plus and minus 15 volt outputs. And that is achieved easily enough because you've got the supply coming in through this resistor and through that resistor from the negative supply, two 15-volt Zenas, a small filter capacitor, and that's your plus 15 minus 15 volt output. This stage here works only on the positive, from the positive supply, and it's producing a 24 volt output and a 24 volt reference sense for this Zena diode. We saw in the previous block diagram how these things are interconnected, but very simply you've got the Zena diode, it gets biased, produces 24 volts over there, 23.6 volts over there, which is your so-called 24 volts. All good there. Now the final stage is the most important one. This thing is the part of the circuit that produces your positive regulated supply and negative regulated supply. Now this top section here is mirrored in the bottom section. So one is producing a positive supply and the other one's producing a negative supply. They are identical in function and opposite in terms of the type of components you've got. So where you have an NPN transistor over here, you've got a PNP over there, you've got a PNP over there, you've got an NPN over there. That's simply because of how the supply is feeding it. So if we look at one half of it, we'll understand how the other half works. And very simply, it's 70 volts is at the top here, ground's at the bottom here. It starts off with this Zena diode being biased through that line there. You've got a 10K, 100 ohms, through the Zena, the low resistors at the top. So the Zena is actually close to the top supply, so you subtract from 70, you subtract the 5.1 volts, and you also subtract whatever voltage drop you have here, but it's very small. So effectively what you've got here is 70 volts minus about 5.1, 5.2. So you've got, let's call it 5 volts. You've got 65 volts over there. That is smoothed by that capacitor. And then that thing acts as the driver for the base of this transistor. So you have one drop, forward voltage drop across that base emitter. And so over here, and if you remember, this is a PNP, so if you've got 65 volts there, you'll have 65.6 or so, 0.7 over there. You've got another base emitter junction over here with a 0.6, 0.7 volt drop, so 66.4 over there. 66.4 over there, you're basically getting that as your regulated output. What it's doing is it's producing a bias to this transistor, and this transistor acts as the pass transistor, producing your regulated output there. Now this will be pretty well regulated because you've got this capacitor there, that capacitor there. So basically those capacitors filter out any changes, rapid changes that you might get to your positive supply over there. And the idea is precisely that. Why would you need this in the first place? Well, this thing's been fed by the plus 70 minus 70, which is your main supply, which also supplies the output boards. That supply is very heavily filtered with those huge capacitors, but it's the output board that is drawing massive amounts of current when you're actually playing music. And that means that that supply will suffer some kind of, fluctuation, albeit quite small because of the filtering effect of the capacitors. But you still want to make sure that your driver section, preamp section, if you want to call it that, gets an incredibly well-regulated, well-stabilized supply and not affected by those dips that the draw of current from the output board would cause. So this is what this does. And it's not really important whether this plus reg V is an exact amount. What this will do is it's going to cause or create a regulated voltage which is a fixed differential from the top. So it'll be lower than the top one by a fixed amount, in this case about 5.1 volts. And the important thing is that it is stable regardless of whether it's minus, whether it's 65, 66, 64, 60, whatever. It's really important that it's stable, but not so important that it's an exact definite value like 65 volts. It doesn't have to be. In fact, it can be a hell of a lot less. Not more because of the components used, but it can be less. And this is important because what it allows you to do is when repairing this board, you can actually feed that there, the power, the plus and minus supply, with values other than the 70 volts, which is exactly what I did when I was repairing this board, because this is the board that had suffered the most, or not the board, this is the part of the circuit that had suffered the most. And what I did is I put using a lab supply with current limit, I put a minus supply on there. I think I used 24 volts, plus 24, minus 24, reference to the ground, and I was able to test as I went along. And although it's a hell of a lot lower than 70, it's still enough to see that the circuit is functioning properly. For example, you wouldn't get 15 volts and minus 15 on here because the current through that resistor wouldn't be enough to actually take the Zener into its proper breakdown voltage. But you will see that that voltage is the exact opposite of that one, so you know that's working. You would also see that the output there is, well, not 24, but close. It's going up as you increase the supply voltage, so you know that that circuit's working. And more importantly, in this particular case where the current is actually supposedly going to be quite high because of those past transistors and it's actually the supply itself, you can keep an eye on the current draw from the positive supply and from the negative supply and make sure that there's nothing going crazy over here. And it happened in this case. I had, I think I had about 20 milliamps being drawn from the positive supply, and this thing was going up to 170, 180 milliamps. So I knew there was something wrong with the circuit. It happened to be that transistor and a bit of leakage on the other ones. So I was able to do the repair, make sure that I had these things stabilized, and I was fairly confident that if I supplied this now with the full 70 volts and minus 70 volts, that I wasn't going to get a lot of smoke coming out. And that's exactly what happened. So that was the important bit on this one. If this had been a finite voltage, like if this thing had been set up to produce exactly 65 volts, I wouldn't be able to do that because the Zeners that they'd use over here would probably be 65 volt Zeners, and I would never get them biasing with the 24 volt supply. Because it's producing a voltage which is 5 volts lower than the supply voltage, it was fairly easy to test. And I could actually check that this plus V equals minus V. And if I increase the supply, decrease the supply, these things were going up and down in tandem with each other, which meant that the whole thing is working fine. The next one is the DC servo detect board, or not board, but section. And what this does is it has a sense line over here, which is from your output, which should be damn close to 0. You know, it's going to go up and down a few millivolts, but it should be damn close to 0. So this signal would come in, go through there and into the one input of the op-amp. Then you would get your, let's see, here it is, plus minus supply over here. You've got a 1 meg pot between them. The wiper goes off there through another 1 meg resistor and it goes to the other input of the op-amp, but there's a voltage divider to ground of 511 ohms. Now this means that whatever voltage you get here, and if it's right in the middle, it'll be at 0 volts because you've got plus 15, minus 15 on the opposite ends over there and there. If it's exactly in the middle, it'll be 0 volts. But if it's, say, at 1 volt, what you're getting is 1 volt over here going through a 1 meg ohm resistor and 500 ohms to ground. So this thing is taming it or attenuating it by, what is it, 20 times, right? Yeah, 20 times. So you can actually have quite a big movement over here for a very, very small adjustment on here. And that's important because you're looking to adjust in the millivolt range as a DC offset, which will come out at this end. And that end, that there, well, then comes out here, goes through there, and that's your plus DC adjustment to the input, as we saw on the block diagram. The opposite, this signal comes from here, it goes into there, it gets inverted, and you get the opposite amount coming out there. Now, what they do want you to check is that you should never get between pin 1 and pin 7 more than 5 volt offset, because that means it's adjusting so much because you've got so much instability in your circuit that something else is wrong. However, this thing was giving me a bit of trouble. Whatever I did here, I could never get this pin 7, the output, to unlatch from one of the supplies. I can't quite remember if it was the positive supply or minus supply. So I was getting like 14.5 volts all the time.
which told me this thing wasn't functioning well, provided, of course, the inputs were fine, and I checked those. So this op-amp was buggered, and that's the one that was changed, and if you recall, that's the one that's now on a IC socket on the board. But once I replaced that, it's a very simple op-amp, TL072, this thing was working fine. The next board was the relay driver, and what the relay driver does is it takes signals from the temperature sense, which is a component stuck to the heatsink by the output transistors, so that if the temperature exceeds a set amount, the relay will trip out and prevent damage. The other sense would be what would it take? It would take the DC detect from the previous circuit, and that would tell it to switch off as well, because obviously there's DC offset, unacceptable DC offset at the output. So this basically does a protection. The testing this board was slightly more difficult, but once I tested the function of the op-amps and found that they were fine, the rest was just checking that the components were okay, and that was pretty easy to do, so that was checked and considered to be in order. The important part is actually the input amplifier, and that takes your negative input, positive input, minus input from the XLR, and there's the differential pair over here, and it's fed by a constant current or current mirror over here to make sure that the current going through here is identical to the current going through there. That's actually set up so that this is fed by a current source over here, which is created by this Zener. If we look at the bottom one, it's actually easier to figure out. You got minus, call it minus 70 volt. It's not, it's minus 65, right? 65 volts over here. The Zener creates a drop of 6.8 over there, so you've got 6.8 volts between that and that. There's a 0.6, 0.7 volt drop, so call it about 6 volts here through 750 ohms. So you get about, I think it's 8 or 9 milliamps. That sets a constant current. That current is pulled, if you follow this here, follow that there, pulled, force pulled through these two transistors. These two transistors are fed by a current mirror, so whatever current's in one is going to be in the other. And so this whole thing is balanced, and balance is the key word. This is more difficult to test because it's not really referenced to ground. It's sort of floating at a base level of ground. And depending on how these transistors are matched to those two, and how these are matched to each other and to those, the output will either be actually around the middle, in other words, the positive drive that's produced finally over here and the negative drive should be an equal amount away from ground, positive and negative. But it all depends on the balance of all these transistors you've got here. And what I found is a lot of them were actually not functioning quite well. These two, for example, have to be identical. If you find that the readings between one and the other are slightly different, in terms of gain, in terms of leakage, in terms of voltage drop, forward drop, then you have to change both. And if you change these two, then you should also change those two so you can get a good balance between the positive and the negative. However, if something is wrong with these transistors, it means that they've been stressed, and it means these two have been stressed as well. If these two have been stressed, or either one has been stressed, you change both. If you change both of these, then you've got to change both of those so that everything matches. When I say it matches, it means you get components that are, in this case, PNPs and NPNs, opposites, but if they're from the same manufacturer, the same, job lot, you'll find that their characteristics match better than if they're from different sources. And so it was best to change them all. However, there's something else. If these two have been stressed, then you see that this is fed down here by that transistor. If those have been stressed, this has probably been stressed. So you change this one. So if you change this one, you change the top one. What I'm trying to say is, at the end of the day, the conclusion I arrived at was that it was easier to change all these transistors. And that's exactly what I've done. The Zeners have been changed because I really don't trust Zeners. I don't trust diodes in general after a few years. Well, a few decades in some cases. So all the semiconductors here have been changed. Resistors that were blown out were repaired or replaced. Some of them were just replaced to make the whole thing more uniform and predictable. And the result is, which we will see, this thing's working perfectly well. So, enough waffle, time to show you the setup. I've connected that the right channel, which is the one that hadn't tested yet, the one with the more damage. I've connected that up and we'll go through it and see how it functions. I also want to show you how some of these adjustments are made to ensure proper zero offset at the output, as well as we've got the output DC offset to adjust to null out. We've got the DC at the input, the positive input and negative input with reference to ground to adjust. And that's important because those are those pots that are on the top of that board. And then obviously there's the idle current to adjust for the amp board. So we'll see that when I've set this whole thing up. Right, we have everything set up for testing. I'll give you a quick view of what's been, how this thing has been set up. But to start off, we've got the output to the speakers, one of the speakers. I'm just connecting one channel at the moment. I have the supply on. I have a XLR connector here. Now, this is a special case. This XLR connector is actually coming from this adapter, B&C adapter to XLR connector, which I made. And this is special in that what it does is it takes the one signal and makes it the hot signal on the XLR, and it takes the other signal and makes it the cold or the negative signal on the XLR, and then you got the common ground. And the reason is I have a signal generator app on my iPad producing a balanced signal. Now, I've done a quick video on how that is achieved. It's basically by using the signal generator app on the iPad, or an app on the iPad, and producing a stereo signal which is 180 degrees out of phase, and using those two, the left and the right, as the hot and cold. If you want, look at the video, I'll link it up above. It's actually quite useful. And the reason I'm doing that is because I don't want to send a single-ended signal only to the amp, because I want to make sure that it works properly. Afterwards, you can actually put in a single-ended signal by shorting the cold signal pin 3 to pin 1, which is ground. But that's what we have set up at the moment. There's one little detail that I want to show you before we start. I did mention before that these wires were connected wrong, which just made it impossible to work. But there was one other problem here, and that had to do with that pot. Fortunately, I checked. This pot sets the idle current on the output transistors, and it's a 500 ohm pot set up as a variable resistor. So it's got the two pins together, and it sets between 0 ohms and 500 ohms. Now, I was just checking, and I found that I was getting 500 ohms and that it wasn't variable at all. And then I went and looked further and found this. The middle pin, the wiper pin, had broken off. It was on the board, but completely broken off the spot, which means the thing was set to maximum. Now, I haven't really studied the circuit enough to know whether maximum setting would have given the maximum idle current or the minimum idle current, but either way, that was definitely not a safe thing to have. So that's been corrected. I've replaced the pot, I've done the wiring, I've connected the board to the front of the amp. This side is completely disconnected. Those two supply lines have been isolated. I don't want any supply on this side. I'm just doing that channel. There you go. So I'm going to set up the iPad app with a balanced signal, 1 kilohertz signal, very low level, and we'll see if we can hear something. So here we go. We've got a 1 kilohertz sine wave. It is at a very low level because, as I mentioned in previous videos,
This is a power amp. There's no volume control. Whatever you feed in, it just amplifies. The left and right are activated, so I've got a stereo signal coming out, but I've got this up 180 minus 180. There's something wrong with this, and I explained this in the video where I describe how I set this up. It's supposed to be plus 90 minus 90, but I've checked, it's working perfectly. I'm getting a stereo signal, 1 kilohertz, and the left channel is the exact opposite of the right channel, which is the true definition of a balanced signal. So what we need to do now is switch it on. I've got this connected with 2 lamps in the limiter. I have limit on, and I'll put that on. Actually, I had 4 lamps. Good thing those things light up. Now what I'm going to do is I'm going to switch this on. Now it's going to flip around before it actually charges the capacitor bank. It's going to take a while, but it'll get there, and then I'll reduce the limit. So let's see. Here goes. Okay. The output, the relay comes in. I've reduced the limit. There's still quite a fair limit on there. The LED here, you can't see it, but the OK LED is on, and I'm going to put on activate the signal. And we have noise. We have our signal. Brilliant. So that's working. Ha! This is so satisfying. Let's see what we're getting on the scope. What we have on the scope is the sine wave. Now it's very low level. So what I'm going to do is I'm going to put it on dummy load so we don't have to listen to it. Let me go up here. Increase the level of the input. And it's looking good. 1 volt per division. Five volts per division. And it just keeps going up. And if you see the light bulbs, they're starting to glow. Now let me drop the volume, and the light bulbs dim. If I increase the volume, light bulbs come on. What that's doing is limiting, because there's more current coming through, and as I increase the volume, the current demand is much higher, so it actually drops the voltage going to the amp. At the moment it's 200 volts. So I'm going to push bypass so we get our full main supply, and we can in fact now increase the volume level without the supply voltage to the amp dropping. Here we go. Let's put it on 10 volts per division. I'm not going to go all the way. Whoa, because I have resistive load in there. They are fairly high power, but they're getting warm now. What we're getting on there, this is 8 ohms, so what we're getting there is, well, let's see, it's not much power really. 10 volts is V squared over R, so 12 watts, not much. We can actually go quite a bit higher, 22, and it's staying clean all the way. All the way, and that is fantastic. I am very, very pleased. Very pleased and relieved. You probably detected that. So yeah, all right. Now, next step. Put the other channel together and then do a final test on the amp. But yeah, I'm happy. I'm happy for now. I'll get back again soon.